Are you sure?
Well, it could be easier than Transformers. Nothing's easier. So no, this is not easier than Transformers because Transformers are the easiest. Okay. Induction is what? Yes, everybody thinks it's difficult. Okay. Is this on yet? The heck? Come on you go. He is okay.
Push.
Please don't be weird. Okay. Coulomb's law. What?
Name of a human.
Yes. This is a human called Coulomb. Yep. Not a robot. Yeah. Okay. Not a robot. Alright, got that? Coulomb's law. So, let's have a look at Coulomb and his law. So remember that a point charge will produce an electric field. Of course. And we had a look at the forces. Let's have a look at that in a bit more detail. So, for example, let's say here is a big Q1 charge, and here is a little Q2, for example. Now, let's just say this is positive and this is negative. So this will be pulled towards this one here. Agreed?
Yeah.
So there's a field around this Q1. And do you remember what the strength of the field is?
Strength.
Yeah, it's the K, which is the 1 over 4 pi epsilon 0, Q1 over R squared. Yeah? But I want to know what the force is. So we have another formula. If you remember, we also have E equals Q over F. Oh, sorry. No, I know. E equals F over Q2. Yeah. Thank you. So we can say that F equals E Q2. But this is E.
Oh.
So we can say F equals K Q1 Q2 over R squared.
Is it?
This is Coulomb's law. It's the force between two charges.
Previously when we used...
It's not really a new law. We've just put two laws together. But it's called Coulomb's law. Because, in fact, I believe this law was discovered before the other two. Yeah.
Before the saturated.
Yeah. It's a bit like actually how Kepler's laws were before Newton's laws. Even though Kepler's laws are just simple examples of Newton's law. Oh wait, have we not done Kepler yet? Oh no, we have. Hang on. Kepler is... Oh, Kepler's later. You don't know who Kepler is. Okay. It is later in the chapter.
I thought that...
No. Okay, sorry. I forgot Kepler's later in this chapter. Okay. I probably have it written down quite neatly here. Yeah. K Q1 Q2 over R squared, where F is the force between the Q's and R is the distance between them. K is a constant. Yeah. Well, that's the proof. It's a very simple proof, and that's the formula. And remember, the K is on your calculator like this. 1 over 4 pi. What number is epsilon? 20 something? 25? No, I want the epsilon. 32.
Yeah.
There, this Bruce, this is what I wanted. This is big K. See, it's the same as this. In fact, your calculator does not have the big K constant on it. If you want the big K constant, you have to type it in like that. The big K constant is in the formula book though. Got that? Yeah. Shamsa, you look exhausted. Were you in Starbucks last night again? Are you sure? What time did you sleep at? 1. What time do you wake up at? 10. Oh, that's loads of time. 10. Okay. We got this? Yeah. Yeah? Okay. That is Coulomb's law. Okay. Here is an example of when you can use Coulomb's law. So, here there's a force. The electron is being pulled to the proton. How big is this force? Well, it'll be the charge of the electron times the charge of the proton over the distance squared. That's the force pulling it in. But the proton also feels a force. Which direction is this force moving? It'll be towards the electron. Yeah? Now how big is that force? Well, that'll be the charge of the proton times the charge of the electron over the distance squared, which is the same. So maybe there's 1 Newton being pulled here and 1 Newton here. But if the forces are the same, then why is it that the electron moves and the proton does not? Now we've actually talked about this before. It's because of the mass. The proton is heavy. It's hard to move it, even though the force is the same. Easier to move the electron. In fact, the electron is 1,000 times smaller in mass than the proton. But we talked about this actually previous class. So we've explained that. So often we imagine the proton is actually fixed. We only really look at the force here. Okay, now when one charge is trapped in an orbit by another charge, then it will have negative potential energy. And again, we talked about this before. Negative means it's trapped. And in fact, we can calculate it. It's equal to minus k QQ over R. No square.
Why R?
And not square?
Yeah.
It's complicated.
But you can make it.
I can give you the answer, but it's too difficult for you.
You can make it easy.
I can't.
You can.
Oh, I wish I could, but I can't.
Simply. Just 2 words.
Before I continue, I'll answer you in a moment. Before I continue, just to be a little bit clear here. Oh, sorry. In my head, I imagined a picture like this, where we have the Q is, for example, positive, and this Q, for example, is negative, and it's trapped in an orbit, and the potential energy is minus K Q over R. And here I don't have the signs, because I already have the sign I want here. So of course, these have to be opposite in sign, because it couldn't be trapped if it wasn't. What happens if both of them were positive? Is it trapped? No, it'll be pushed away. Okay, so this is when it's trapped. That's the only situation we actually care about, because this is the one you study in chemistry when you talk about ionization of electrons. You know, the electron is trapped around the proton. How much potential energy does it have? It has this amount, which is a negative. Is that okay? Yeah. So in fact, this here is the ionization energy. You've done ionization energy in
Yeah.
chemistry? Yeah. This is how much the ionization energy is. You can see it depends on the charges and the distance from the electron to the proton. So is it easier or harder to ionize an electron who is in a high orbit or a low orbit? Which is easier, the high or the low orbit?
High.
The high orbit.
Yeah.
Now, if the orbit is high, then the radius is big or small?
Big.
Big. And if the radius is big, is this big or small?
Small.
Small. Therefore, less ionization energy required. Okay, so the formula makes sense. Now your question is, why is it or and not or squared?
Yeah.
Okay, no. I have a simple answer for you.
Okay.
I have a simple answer for you. Can I go to the notes? Right. So I want you, what was the units for the K? Did you write them down?
Yeah, and m square c minus 2.
Okay, so the potential energy has a K, it's a Q1, a Q2, and it has an OR, and we don't know the power. So I won't say the power. Happy? Okay.
Oh.
Now,
Oh.
what's the units for the K?
N
M
square.
Is it?
Yeah.
I don't think it's that.
Why?
I wrote it earlier. There it is.
Yeah.
Oh, sorry, I apologize. I thought you were finished. NM squared.
C minus
Yeah. And what's the units here?
2. C square.
Yeah. And what's the units here?
M.
MN.
Yeah.
Because we don't, this could be squared, it'd be meters squared.
Yeah.
Cube, meters cubed. And what's the units here?
Joule.
Joules. And they should be equal.
Yeah.
Right, so this cancels this.
Okay.
Hold on, no, I'm not finished. And this is NM2 minus N. And this is joules.
Yeah.
But joules is the same as
And then.
NM. So therefore, the N has to be 1. Now, are you happy?
Yeah.
You should be very happy.
Yeah.
It's a brilliant reason.
Yeah.
Okay, so continuing now. Right. Coulomb's law gives the size of the force between two charges. This force is actually one of the 4 forces of nature. In nature, there are 4 basic forces. You actually know one of them already.
Gravity.
Gravity is one of the forces.
Yeah.
There's 4 forces in nature. Gravity is the first one. The second one is this force, this Coulomb's force, the force between charges. Okay, this is the second one. We will study the other 2 in the next chapter. Okay, in the atom. Yeah. So this is one of the 4 forces of nature. And Coulomb's law is an example of an inverse square law in physics. These are actually pretty common in physics, and it's worth looking at the reason why. So what do I mean by an inverse square law? Let me explain that. Coulomb said F equals K Q1 Q2 over R squared. Now, this K is just a constant. It doesn't really matter. It just, it's what units we use. So we can forget about that. And this Q, this makes sense. If the charge is bigger, then we should have more force. That makes sense, right? And this Q also makes sense as well. So the real question is, why do we have a square here? A lot of formulas in physics will have a square in the denominator. Later in the chapter we will study Newton's gravity formula, but some of you might have seen it before. Maybe. Anyways, my point is, why is it so common to get a square in the denominator? Why do we keep seeing squares here in physics? So, here's a simple example why. Let's say I have a student here, and I have another student here. And let's say this student has a smell, they're smelly, and this student also has a smell, they're also smelly, okay? And this student wants to know how much smell they can smell from this student. Okay. So, we'll choose a unit for our smell. It doesn't matter. We'll call them Stephen smell units, SSUs. Okay. So, the smell comes out of the student. Now, if this is bigger, is there more or less smell here? There's more. So, we think the formula for how much smell he smells will be an S1 in it. But also, you know, other things too, like how much does he smell? You know, maybe this guy smells really good and cancels some of this smell. You know, or maybe it makes it worse. Anyways, whatever. I really care about why do we have the R squared. So, if you look at the shape here, let's say this is one SSU. This is one SSU. It's coming out of the person. This here, what shape would this be? Yeah, or rather it's 3 dimensions. So what's that shape called in 3 dimensions? A sphere. Now, as we get further away, is the smell getting bigger or smaller? Well, it's actually staying the same, but what's happening is it's being spread out over a bigger distance. So, for example, this is one SSU for this distance, then for this one, and then for this one. So by the time it gets to this person, he will get one SSU divided by whatever the area is for the sphere. And what's the formula for the area of a sphere? It's 4 pi r squared. So the reason we have the r squared is because we imagine it as like a ball that gets bigger and bigger and bigger, and it reaches out to the person. And when it gets to the person, the amount gets reduced because it's spread over a bigger area. And this is kind of like what's happening with Coulomb. The charge and the force is spreading out over bigger spheres. And when they reach the end, you know, you only care about how much you have when you get to the end for the piece you're looking at compared to the total. So the reason for the square is actually because it's the volume of a sphere. The 4 pi is kind of being eaten by the constant. It's entered into the constant. You don't need to write this down. I'm just telling you, when you study physics more and more, you'll see the r squared quite a lot, and this is kind of a reason why. Yes, I already looked at an example. Before I continue, I want you to notice the K is very large. Well, what was it? It's very large. That will be important later. Okay. Right. Here's a very simple one I want you to try. You have a proton, you have an electron. They're 0.1 nanometers apart. What's the force? Use Coulomb's law. Give me the force.
What's the K? 8, 9.
Got an answer?
Yeah. Small.
Should be small. The charge is 27. No, 23, isn't it? Okay, do we get an answer?
Yeah.
What you get, Bruce?
No.
No answer, why not? This formula, isn't it? K Q1 Q2 over R squared. Yeah, proton and electron. Right. Got -8 here. Oh, something else. The charge, is it? Oh, goodness. I don't know, because I always use the constant on my Here, no, I'll tell you. Wait, I'll tell you right now. 19. Right. Did we get this for the fourth?
Yeah.
Did we get this?
I got this one now.
What happened?
Let me retry.
Come on, this is an easy one. What's going wrong? Did I type something wrong? I don't think so.
No.
Yeah? Not this? Audrey, did you get this? Yeah. Negative what?
18, you didn't steer. I steer.
Oh, did you square the or? Maybe.
What?
I steer.
I'm gonna get this one.
Ah, guys, what's wrong with you?
Because you buy two. You have to
No,
steer two.
no. It's not E times 2, it's E times E.
Oh yeah, square.
Yeah.
Square. Oh my god, yeah.
Oh dear. Did you get this, Bruce?
Yeah.
I hope so. Did you get this? Okay. Continue. Okay. I can see people's brains are starting to stop functioning. Do you have a class after this one?
No.
Oh. Right, we still have two more examples to do. So, how long does it take an electron to orbit a proton when the distance is 0.2 nanometers?
This is kind of
Yes.
circular motion.
It not only is it kind of circular motion, it is
Is.
circular motion. Right, let's have a look at this circular motion one. So you've got an electron going around a proton. Let's see. Right, so we have our electron, we have our proton, and around it goes. And the distance is 0.2 nanometers. And the question is, what is the time?
Find T.
Time t. Right, so we know that F equals ma, which equals m
We scare.
b squared over r, which equals m, and b is omega r squared over r. Yes? So in other words, it equals m omega squared r. That's the F. But maybe you knew that already.
Yeah.
Anyways, Coulomb also gives us a formula for F. Coulomb says the F is K, Q1, Q2 over R squared. So therefore, I can say K, Q1, Q2 equals M omega squared or cubed, if I just bring that up. So, I can say omega equals, let me see, that is K, Q1, Q2 over M R cubed square root. But T equals 2 pi over omega. So finally, I can say the time will be 2 pi root mass of the electron, radius cubed, K, charge of electron times charge of proton. So that would be E squared like that. Yeah? 2 pi square root mass of electron times the radius cubed, which is 0.2 times 10 to the power of minus 9, all over K, which is 1 over 4 pi epsilon 0. No, what's epsilon 0? 32? Times E squared. What?
Yeah.
What? It's great.
Yeah,
It's great. 1.12 times 10 to the minus 15. Hang on, let me think. micro, nano, nano, pico, femto?
We don't know
Is it femtoseconds? 1.12 femtoseconds?
But we can change the electron for electron scale.
Anyway, so we'll just leave it like that. I like these questions because they mix two chapters together.
It's good, it's good.
I know you like them too.
Yeah. Good question.
Ah, it's a brilliant question. Whoever thought of this question was a genius. Genius, yeah, absolutely, yeah. Alright, do you have this? Yeah. Okay, continue. Yep. Last example now. I think you can do this one. How much energy does an electron have if it's orbiting a proton at this distance? Now, the potential energy, we have the formula for this. It's minus K Q1 Q2 over R. Can you calculate that, please?
Is it not trapped?
No, it is trapped. Oh, if it's not trapped, it should be a positive potential energy.
But still the same formula that we have.
Yeah, I think so. I think so, except the sign is positive. Yeah.
A9A7551
What? That's huge. It should be small.
No, there's K.
Ah, yeah.
Okay. 9A.
Stop talking until you get the final answer.
I have to find the K.
So you have to consider the gravity pull.
That's negligible compared to, yeah. Everything else. Did you get the potential energy? What is it? 1 point times negative. So, because it's a small energy, what would be an appropriate unit to use? Guys, wakey. Hello. If the energy is very small,
EV.
thank you. Electron volts. If the energy is really small, it's appropriate to use electron volts.
Divide by.
Yes, you cannot, because I didn't ask you for it, but for fun, let's see what it is. So, what is the formula? 1 over 4 pi epsilon 0 times Q over R.
Not just Q. Q square.
Oh, sorry, thank you. Q1, Q2. So, square. Minus 18. Yeah.
Divide by.
Did I do something wrong? What's wrong?
It's right.
I got negative.
Yeah? Yeah. Now, that's a tiny energy, so it would be appropriate to use electron volts. So how do I convert this into electron volts of energy?
Divide by 1
Divide by what?
1.
Now, what's it called? Divide by?
Electron.
Divide by?
That.
E.
Yeah. 1.602 by 10 to the minus.
Divide by E. Nice. 9.6 electron volts. So the potential energy equals 9.6 electron volts. This is also called the ionization energy. Do you use any special letter for ionization energy?
Yeah. I.
Really?
Yeah.
Really? Fine. Ionization energy equals 9.6 electron volts. Is this true?
I don't know.
Is he telling me a lie? 9.6 electron volts is the energy needed to free this electron from the orbit of the proton. Do you discuss the energy levels in chemistry? Like,
Yeah.
you do, but do you mention how many electron volts it requires or anything like that? So how do you measure ionization energy, or you don't?
Yeah. We do.
But what unit?
Joule.
You use joules in chemistry?
Yeah.
For this too? For ionization energy?
Yeah.
Are you sure?
Yeah.
I don't believe you.
Just believe me.
But then, hang on, wait, don't listen. The energy must be very small then. So, you must have something like 10 to the power of minus
Yeah.
20.
Yeah.
This is what you do in chemistry.
Yeah.
Really? You don't use electron volts?
Yeah, we do.
That's disgraceful.
Believe me.
Believe you? When did you do this?
Last semester.
Do you have your notebook?
Now?
Yeah.
I didn't have now.
Anyways, we try to use electron volts when it makes the answer nice and neat like this. 9.6 electron volts. Yep.
The answer be right. Should the answer be right?
No, it shouldn't. But if there's an opportunity to make it neat, we should use it. Yeah. Okay, yeah.
Do I happen to change it?
No, it doesn't matter because I never asked you explicitly to do this, so it's okay. Right. Here you go. If you want to take a picture of these questions, this will be your homework then, which you can start for 5 minutes.
Library.
What? Can I close this? Can I close this?
Yeah.
Yep. Just try these for 5 minutes, okay?